Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Today we will cover a topic Fourier transform infrared, which is called as a FTIR. For the introduction, what is infrared? Infrared refers to that part of the electromagnetic spectrum that we have learned in previous lecture. It lies between the visible and the microwave region. For electromagnetic spectrum, it refers to the seemingly diverse collection of radiant energy from cosmic rays to X-rays to visible light to microwave, each of which traveling at the speed of light. So in our previous lecture, we have determined the UV or ultraviolet light, and we know which light has high energy and which one is the lowest energy. So I hope you will still remember our previous lecture and you can relate that lecture with this topic. So infrared region just below the visible region. As we can look at here, the gamma rays has the highest energy and the radio frequency has the lowest energy. So infrared lies the wavelength is in the between 2.5 to 25 micrometer. And more common units are wave number, which is cm negative 1 over cm, which is the reciprocal of the wavelength in the centimeters. And wave number are proportional to the frequency and energy. And for your information, infrared region is divided into three regions, which are we have near, mid, and far IR. So the mid IR region is of the greatest practical use to the organic chemists. So we only interpret the mid region. Okay. So this is the region of wavelength between times 3 times 10 to the power of negative 4 and 3 times 10 to the power of negative 3 cm. Chemists prefer to work with numbers which are easy to write. Therefore, infrared spectra are sometimes reported in micrometer, although another unit is new, okay, also known as a wave number, is currently preferred. So we use wave number which is cm negative 1, okay, this one cm negative 1. So we can see that the types of energy is different, which is the near one consists highest energy compared to the mid one, because the near visible is approaching the visible light. So we interpret by using the mid region. Okay. So for infrared, longer wavelength and lower frequency than visible light. The normal range of infrared frequency used is 4000 centimeter negative 1 to 400 centimeter negative 1, which is in the range of the mid IR region. Wavelength 700 nanometer to 1 mm. So IR spectroscopy measure the vibration of the atom. Stronger bond and light atom will vibrate at a higher stretching frequency with number. So meanings that the infrared light that pass through the sample, the bond in the sample will vibrate at its own stretching and its own frequency. So the instrument name is the Fourier transform infrared. Unit we use is cm negative 1 or 1 over cm. Wave number is directly proportional to energy, which is higher wave number will produce higher energy. So we use Fourier transform infrared to measure the functional group in the molecule. Okay, let us continue. For example, if you have functional group of glycerol, you have this one is the structure for glycerol. We have three functional group OH, which is hydroxy value. So by using FTIR, you can determine that is there the presence of the functional group in the modification modification of the polymer unit. For example, if you want to incorporate glycerol into the styrene structure, so you need to observe OH functional group by determining the wave number of OH functional group in IR region. So for OH IR region, we can determine by using the appendix, which is in the table of the wave number. For example, OH, it will lie in the wavelength of 300 and 3200 centimeter, -1. So for the structure of styrene, you can observe the structure of CH, CH, and the other structure for benzene ring. Okay, all the CH, NH2, and so on, it has its own wave number. Now we look at the details of the explanation of infrared. It is a common and simple technique to categorize unidentified compounds. So time-resolved measurement can also be used to monitor the changes in the concentration of a given compound. Changes in the concentration are observed by the changes in the peak intensity. Sample can be investigated in the gas, liquid, and solid phases. Depends on the instrument and the ability of the instrument. Sometimes the instrument, for example, in our lab, it can investigate the liquid and the solid phase. And we need a specific instrument, which is we can put the solid into the KBR disk. Okay, we call it as a KBR disk. If the sample is liquid, you can use the KBR disk. If the sample is solid, you can just put it on the plate of the FTIR instrument. However, precautions must be taken to ensure the solvent or substrate absorbent features are removed from the spectra after the experiment was done. Now we look at the specific function of IR spectroscopy. Okay, first one is we want to establish the identity of two compound. If you want to make a comparable study, so you can use FTIR. For example, if you want to make a modification of certain polymer with and without the incorporation of, for example, you want to modify unsaturated polyester resin with coconut shell. Okay, so as we all know, coconut shell contains a silica structure, Si, SiO, and also OH structure, right? If you make a modification. So for the comparable study, you will have unsaturated polyester resin, the pristine or the original of the structure of unsaturated polyester resin, and then the one that you have modified with the coconut shell. So at the modification polymer, so you will have a new peak, which is Si and also OSI, and together with the OH, right? So you can make a comparable study if the presence of OH at the unsaturated polyester resin. So it means that coconut shell is homogeneous or well dispersed in the polyester resin. So the modification is success because the presence of new peak in polyester resin. Okay, for second function, we want to determine the structure of a new compound from its functional group. So as I mentioned, if you done the modification of that polyester resin, you can determine the new peak presents on the new modification polymer. Third one, we want to determine the nature of contaminant in a sample. Okay, if you have a sample of food sample, for example, oil. Okay, at the oil, you want to know is there any contamination in the oil? For example, is there any presence of the acid or so on? So you can determine the functionality of that contaminant. make sure you know the structure or the contaminant that might contaminate your sample, okay, for easily determination. And we also use FTIR to quantitative analysis of a component in the overall mixture, and for the quantitative analysis of contaminants in a given sample by observing the area below the graph. All right. Why infrared spectroscopy? Infrared spectrum represent a fingerprint of a sample with absorption peaks which correspond to the frequencies of vibration between the bond of the atom making up the material. Because each different material is a unique combination of atom, no two compounds produce the exact same spectrum. Therefore, infrared can result in a unique identification of every different kind of material. So every bond, for example, CH, we have NH, we have C double bond C triple bond. All this bond, it has its own wave number. This one is the illustration of IR spectrometer principle. Okay, we have the glowing wire source and the reference cell and also the sample cell, and it also have a monochromator and rotating segmented mirror. Okay, sample will be placed in here, and infrared light will pass through the sample and also through the reference sample onto the monochromator, and result will be detected. We have two types of spectrometer, dispersive and Fourier transform. For dispersive spectrometer, separate different frequency component. So we can determine the absorbent versus wave number, and also wave number versus transmittant. Okay, this one for transmittant. For absorbent, the peak goes upward. For transmittant, the peak will shift downward. This one is the absorption process for infrared. First, beam of infrared light is passed through the sample, and frequency which match the natural vibration frequency of the compound is absorbed. So the molecule in the compound that absorb light will be vibrate, and change in dipole moment of the molecule, and the mode of vibration of that molecule is either bending or stretching. Bending means that like you pull the bond, you pull the material into opposite direction, and it is a stretching. Okay, stretching is you pull the material in the opposite direction. Bending vibration, it will change the angle between the bonds, between the two bonds. Band intensities can also be expressed as absorbent, which is on the y-axis. Absorbent is the logarithm to the base 10 of the reciprocal of the transmittant. So we use transmittant versus wave number, and we seldom use absorbent versus wave number. So this IR spectrum of 14 plotted as transmission left and absorbent right. So actually absorbent is the reciprocal of the transmittant. Okay, dia akan terbalik. Yang ni peak ke atas, yang ni peak dia ke bawah. So for our study, our syllabus, we will determine the peak based on the transmittant. Now we look at the factors limiting the number of absorption band. No change in dipole moment due to the symmetry. This one is example of ethylene and chloroethylene structure. Because of the second factor is because of the weak absorption. Okay, now we look at the modes of vibration. Molecule absorb specific frequencies that are characterized by dry structure.